Imagine the most powerful explosion you can. Now, multiply that by 1,000,000,000. Then, multiply it again by 1,000,000,000. You're still not even close to the unimaginable power of a hypernova. These cosmic titans are the universe's most powerful explosions, dwarfing even the already impressive supernova. Hypernovae are so bright they can outshine entire galaxies for a brief, glorious moment. They release more energy in a few seconds than our sun will in its entire 10 billion-year lifespan. But what exactly are these monsters of the cosmos? Where do they come from? And could one threaten Earth? The answers lie in the heart of dying stars much larger than our own sun. These stars are ticking time bombs, destined to end their lives in a blaze of glory that sends shockwaves across the universe. Understanding hypernovae allows us to peer into the most extreme environments the universe has to offer. They are not just agents of destruction but also cosmic engines that forge the elements essential for life itself. Hypernovae, like their less energetic cousins, supernovae, are born from the death throes of massive stars. But not just any star can go hypernova. It takes a star at least 30 times the mass of our sun to even have a chance of ending its life in this spectacular fashion. These stellar behemoths live fast and die young. Their immense gravity relentlessly crushes their cores, forcing hydrogen atoms to fuse into helium at a furious rate. This nuclear fusion is the engine that powers all stars. But in these massive stars, it's like a runaway train. As the star burns through its fuel reserves, it produces increasingly heavier elements, eventually creating a core of iron. Iron is the star's death warrant. It cannot be fused into heavier elements, and so it accumulates, an inert and growing tumor at the star's heart. When the iron core of a massive star grows to about 1.4 times the mass of our sun, it reaches a critical tipping point. The core can no longer withstand its own gravity and collapses in on itself in a fraction of a second. This collapse triggers a shockwave that travels outward through the star at nearly the speed of light. As the shockwave slams into the star's outer layers, it heats them to billions of degrees. This triggers a runaway nuclear reaction, fusing lighter elements into heavier ones in a matter of seconds. The star becomes a giant fusion bomb, unleashing a blinding flash of light and an explosion that can be seen across the universe. This is a supernova. But hypernovae are even more extreme. They occur when the collapsing core of a rapidly rotating star forms two powerful jets of energy that blast out from its poles at nearly the speed of light. These jets are thought to be powered by the star's immense magnetic fields, which become twisted and amplified during the collapse. The energy released by a hypernova is almost impossible to comprehend. In just a few seconds, it can unleash as much energy as our sun will produce over its entire 10 billion-year lifespan. This energy is released in a variety of forms, including light, heat, and radiation. The most visible component of a hypernova is its blinding flash of light. For a brief period, a hypernova can outshine an entire galaxy. If a hypernova were to occur within a few thousand light-years of Earth, it would be visible during the day and would be brighter than the full moon at night. But the light show is just the tip of the iceberg. Hypernovae also unleash a torrent of high-energy particles, including protons, neutrons, and electrons. These particles travel at nearly the speed of light and can be incredibly destructive. A hypernova's particle storm could strip the atmosphere from planets light-years away and sterilize any life that might exist on their surfaces. Section 5 Gamma-ray bursts death rays across the cosmos. Perhaps the most terrifying aspect of hypernovae is their association with gamma-ray bursts, or GRBs. These are brief, intense flashes of gamma rays which are the most energetic form of light in the universe. GRBs are thought to be produced by the jets of energy that blast out from the poles of a collapsing star during a hypernova. GRBs are incredibly powerful. They can release as much energy in a few seconds as our sun will produce over its entire lifetime. And because they are highly focused beams of energy, they can be deadly even at vast distances. If a GRB were to be aimed directly at Earth from a nearby galaxy, it could have catastrophic consequences. The gamma rays would strip away our ozone layer, leaving us exposed to the sun's deadly ultraviolet radiation. The GRB would also trigger a global EMP, knocking out power grids and communication systems worldwide. It's a good thing that GRBs are rare events and that the chances of one hitting Earth are extremely slim. Section 6. Hypernovae near Earth. While hypernovae are incredibly powerful and destructive events, the The good news is that they are also incredibly rare. Astronomers estimate that only a handful of hypernovae occur in the observable universe each year. However, there are a few stars in our own galaxy that are potential hypernova candidates. One such star is Eta Carinae, a massive star located about 7,500 light-years from Earth. Eta Carinae is known to be unstable and has experienced several outbursts in the past. While it's impossible to say for sure if or when Eta Carinae might go hypernova, it is certainly a star that astronomers are keeping a close eye on. Another potential hypernova candidate is WR104, a star located about 8,000 light-years from Earth. WR104 is a Wolf-Rayet star, a type of star that is known to be losing mass at an extremely high rate. This mass loss creates a dense stellar wind that is thought to be a precursor to a hypernova explosion. While the chances of either Eta Carinae or WR104 going hypernova in our lifetimes are slim, they serve as a reminder that we live in a dynamic and ever-changing universe. Section 7. Cosmic Alchemy. Hypernovae are not just agents of destruction, however. They are also cosmic engines that play a vital role in the evolution of the universe. In the intense heat and pressure of a hypernova explosion, lighter elements are fused together to create heavier elements, including gold, platinum, and uranium. These elements are then scattered throughout the universe by the supernova's expanding debris cloud. In fact, most of the elements heavier than iron in the universe, including the elements that make up our planet and our own bodies, were forged in the hearts of dying stars. Without supernovae and hypernovae, the universe would be a very different place, devoid of the heavy elements necessary for planets and life as we know it. Hypernova are also thought to play a role in the formation of black holes. When the core of a massive star collapses, it can create a black hole if enough mass is concentrated in a small enough space. The intense gravity of a black hole can then warp and distort the fabric of space-time, creating some of the most extreme environments in the universe. Section 8. Seeds of Life and Destruction. The impact of hypernovae on life in the universe is complex and multifaceted. On the one hand, the intense radiation and gamma-ray bursts associated with these events can be deadly to life as we know it. A nearby hypernova could potentially sterilize entire planets, wiping out any life that might exist on their surfaces. On the other hand, hypernovae are also essential for life as we know it. They are the cosmic furnaces that forge the heavy elements necessary for planets and life to exist. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all created billions of years ago in the hearts of dying stars. Furthermore, the shock waves from hypernovae can trigger the collapse of gas clouds, leading to the formation of new stars and planetary systems. In this sense, hypernovae are not just agents of destruction but also engines of creation. They are a testament to the cyclical nature of the universe, where death and destruction pave the way for new life to emerge. Section 9. Searching for Cosmic Catastrophes. Astronomers are constantly on the lookout for hypernovae, using a variety of telescopes to scan the skies for these powerful events. One way to detect a hypernova is to look for its extremely bright flash of light, which can be seen even in distant galaxies. Another way to detect a hypernova is to look for its gamma-ray burst. GRBs are the most energetic events in the universe, and they can be detected by satellites designed to monitor gamma-ray emissions from space. By studying hypernovae, astronomers hope to learn more about the lives and deaths of stars, the evolution of galaxies, and the nature of the universe itself. These cosmic cataclysms provide us with a glimpse into the most extreme environments in the cosmos and remind us of the incredible forces that are at play in the universe around us. What other mysteries do these cosmic explosions hold? The universe is full of wonders, and hypernovae are a stark reminder of the power and beauty that lie hidden within the vast expanse of space.